Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Atika binti Muhammad Nazir. My matric number 255924. Today, my group member Nur Jamila binti Adnan, Nur Amira alias and Muhammad Daniel Zikri and I will present about our topic, which is transportation application, Top Speed Bicycle Company. Okay, as for the introduction, we can say that the Top Speed Bicycle Company has manufactured and market a line of 10 speed bicycles, and this one also has final assemblies planned in 2 cities, which are the labor costs are low. Other than that, there are 3 major warehouses near the large market, which is Chicago, New York and Los Angeles. For the factory, there are 2 factories in New Orleans and Omaha. The factory capacity is for New Orleans is 20,000, while for Omaha is 50,000 only. Okay, moving for the next slide. This shows about the supply, source, destination and demand of the Top Speed Bicycle Company. This company wants to develop a shipping schedule that will minimize the total annual cost.
Continue for the linear programming model is LP model. The variable is X1, the number of bicycles shipped from New Orleans to New York. X2 is the number of bicycles shipped from New Orleans to Chicago. X3 is the number of bicycles shipped from New Orleans to Los Angeles. X4 is the number of bicycles shipped from Omaha to New York. X5 is the number of bicycles shipped from Omaha to Chicago. X6 is the number of bicycles shipped from Omaha to Los Angeles.
I will continue for this slide. In this slide, we will to talk about objectives and the subject too. So for the objectives, the company wants to minimize the total shipping cost. So in this slide, we select minimize Z. Z represents the total shipping cost. So minimize Z equal to 2x1 plus 3x2 plus 5x3 plus 3x4 plus x5 plus 4x6. This is the objective for this problem. And the second, I would like to talk about the constraint. So the first constraint is x1 plus x4 equal to 10,000, represent the New York demand. And the second constraint is x2 plus x5 equal to 8,000, represent the Chicago demand. And the third constraint is x3 plus x6 equal to 15,000, represent the Los Angeles demand. The fourth constraint is x1 plus x2 plus x3 less than equal to 20,000, represent the New Orleans factory supply. And the fifth constraint is x4 plus x5 plus x6 less than equal 15,000, represent the Omaha factory supply. And for the last, all variable is greater than equal to 0. So I will continue for the solution into M for Windows. From the model that we get before, we transfer into the QM for Windows to get the output. As you can see from the slide, the table is the output from QM for Windows. So we see the optimal solution, which x1 equal to 10,000, x2 equal to 0, x3 equal to 8,000, x4 equal to 0, x5 equal to 8,000, and the last is x6 equal to 7,000. And from the table, we can see the total shipping cost is 96,000 in dollars. From the table, we can see in the column right hand side. For the transportation problem, it's a special case of LC as the coefficient for every variable in the constraint equal to 1. For this transportation problem, we need to do a sensitivity analysis. For the sensitivity analysis, have two. The first one is the objective function coefficient, and the second one is the right hand side value of constraint.
Okay, now I will continue present the part of objective function coefficient. Okay, from the QM for window output, we can see that the minimum shipping cost on X1 was $2 and the minimum shipping cost on X5 was $1. which are indicate as the original value in the output. Okay, this objective function coefficient has a lower bound of negative infinity and the upper bound are $4 and $2 respectively. Okay, this means that the current corner point solution remain optimal as long as the minimum shipping cost on X1 does not go below $4 and the minimum shipping cost on X5 does not go below $2. Okay, the minimum shipping cost on X2 and X5 have an upper bound of infinity, which it may increase by any amount, and a lower bound $2 and $1 respectively. Okay, lastly, the minimum shipping cost for X3 and X6 were $5 and $4, which are indicate as the original value in the output. Okay, this objective function coefficient has a low bound of $4 and $3. This means that the current corner point solution remain optimal as long as the minimum shipping cost on X3 and X6 does not go below $6 and $5. In order to minimize the shipping cost, we decide to change in objective function coefficient. Okay, we change the X2, X3 and X6 from $2, $3 and $5 to $1, $3 and $2 respectively. So finally, we can reduce the shipping cost from $96,000 to $58,000. Okay, from this new output, we can see that the minimum shipping cost on X1, X2 and X6 has a lower bound of negative infinity and upper bound are $3, $1 and $3 respectively. Okay, this means that the current corner point solution remains optimal as long as the minimum shipping cost on X1, X2 and X6 does not go below the upper bound. Okay, the minimum shipping cost may increase any amount as indicated by the negative infinity and the optimal corner point does not change. Okay, the minimum shipping cost on X3, X4 and X5 have an upper bound of infinity, which is it may increase by any amount, and the lower bound are $2 for X3 and X4 and $1 for X5.
So Assalamualaikum. So today I'd like to continue our presentation. So we already got the optimal value for this equation. So we like to know that what will happen when we change the right hand side value of the constraint. So in this equation, the right hand side value of the constraint is represented as the number of bicycles or the number of resources. So you can see, as you can see, when we use the QM for Windows, especially when we look at the original solution, we already know the upper bound, lower bound and the original value. So the upper bound will give us the maximum number that will give the feasible solution in the graph. The same goes to the lower bound that will give the minimum number for the feasible solution in the graph. As an example, when we can see on the constraint number 4, the upper bound is the infinity, which is we can put the number until the infinity. But in this solution, we want to use the minimum value that will cost us to do a shipping cost. So as you can see, when the number of bicycles of the warehouse in the New Orleans above the 20,000, then the objective function will no longer increase by the dual price. This will be the excess of the resources. Why? Because the dual price is relevant only within the limited sensitivity analysis about how much more our resources will be useful. Next, you can see while we changing the right hand side value of constraint, we can minimum the cost of the shipping for this solution. Like we can see the change of the right hand side value of the constraint where the number of bicycles at the warehouse of Omaha is 23,000. This will make the shipping cost decreasing from $96,000 to $88,000. But beyond the upper bound value, which is 23,000, then the objective function will no longer increase by the dual price. There will be excess of the resources. Same goes to when we change the number on the constraint number 4, which is at the New Orleans supply. For constraint New York demand, Chicago demand and Los Angeles demand, the upper bound should not pass the amount 12,000, 10,000 and 17,000 respectively. This will be made the insufficient of the warehouse or not as out from feasible region. thus there is no feasible solution.